Hello everyone and welcome to this presentation. My name is Alfonso and today we're going to dive into the fascinating world of computer architecture. Every device we use today, from our smartphones to powerful supercomputers, relies on a fundamental structural design to process information. In this video we will explore and compare the two most influential models in computing history, the von Neumann architecture and the Harvard architecture. My goal today is to give you a clear understanding of how they work, their advantages, their limitations, and how they fundamentally differ. Let's get started. Let's begin with the John von Neumann's architecture, proposed in 1945. The defining characteristic of this architecture is the stored program concept. In a von Neumann system, both the data and the instructions, the program itself, are stored in the exact same memory space. They share a single communication pathway, known as a bus, to travel back and forth for the central processing unit, or also called the CPU. The main advantage here is simplicity. Because there is only one memory block and one set of buses, data bus and address bus, the hardware design is much simpler and cheaper to manufacture. Memory space is also used very efficiently, as space not used by instructions can be used by data. The disadvantages, however, these designs leads to a major drawback, known as the von Neumann bottleneck. Since data and instructions share the same bus, the CPU cannot read an instruction and read or write data at the exact same time. It has to do it sequentially. Modern CPUs are incredibly fast, but they end up waiting idle for the memory to fetch data, limiting overall system performance. To truly understand this, let's look at a practical demonstration using the von Neumann machine simulator. Our goal is to create a loop. We will start with the value of 5, add 2 in each iteration, and keep running some. We will repeat this exactly 10 times. Before I run the simulation, I want to emphasize a crucial detail. Look at the RAM memory layout. Notice how my program instructions like load, add, store, and jump are located right here alongside my data variables, like my counter, my current value, and my total sum. They share the exact same memory space. This is the essence of the von Neumann architecture. Let's run the first iteration step by step. First, the CPU fetches the instruction from memory. Notice how the bus is occupied. We load our current value, which is initialized at 5. We add it to our total sum, making the sum 5. Next, we update our current value by adding 2 so it becomes 7. Then we increment our counter from 0 to 1. Finally, we check if the counter has reached 10. Since it hasn't, the jump instruction sends us back to the start of the loop. In iteration 2, our second current value is 7. We add it to the sum, making the new sum 12, counter becomes 2. In iteration 3, current value is 9, sum becomes 21, counter is 3. In iteration 4, current value is 11, sum becomes 32, counter is 4. As the simulation runs, you can visually see the bottleneck. The CPU must fetch an instruction, wait, execute, fetch data, wait, write data, and so on. They cannot happen simultaneously. Once the counter reaches 10, the loop condition is met, the program halts, and our final total sum is successfully stored in memory. Now let's move on to the Harvard architecture. This architecture was developed to overcome the limitations of the von Neumann bottleneck. The fundamental difference here is separation. The Harvard architecture physically separates the memory used for the data from the memory used for instructions. Each memory has its own dedicated buses. The biggest advantage is speed and performance. Because the CPU has separate pathways, it can fetch the next instruction from the instruction memory at the exact same time it is reading or writing data to the data memory. This parallel processing drastically reduces idle CPU time. The downside, complexity and cost. Having distinct memory modules and a dual bus system requires more physical pins to the CPU. a more complex motherboard design, and ultimately a higher manufacturing cost. Furthermore, free space in the data memory cannot be used to store instructions, which can sometimes lead to wasted space. To summarize, let's do a visual comparison. Von Neumann uses a single unified memory for both data and instructions. Harvard uses physically separated memories. Von Neumann has a single bus system, creating a bottleneck. Harvard has separate independent buses for instructions and data. Harvard is generally faster due to simultaneous fetching, whereas von Neumann is slower because fetching is sequential. Von Neumann is cost effective, simpler to build, and maximizes memory usage. Harvard is more expensive, complex, and requires strict management of separate memory blocks. Today, many modern processors actually use a hybrid approach, a von Neumann structure for the main RAM, but the Harvard structure inside the CPU for the L1 cache, with separate caches for instructions and data, to get the best of both worlds. Understanding these two architectures is key to grasping how computers process information, and how hardware design has evolved to meet our demand for speed. Thank you very much for your time and attention during this presentation. I hope the concepts of the von Neumann and Harvard architectures along with the practical simulator demonstration were clear and informative. Good night.